Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. So, we are in module 12, that is the last week of this course, and this is lecture 4, that is the penultimate lecture, and we are discussing about X-ray diffraction profile and its analysis. So, basically what we were discussing is X-ray diffraction profile of a real specimen and how to analyze that, how to understand various effects that causes this kind of a diffraction profile from a real specimen. So, what we understood by now is that we can construct X-ray diffraction profile for any specimen if we know the crystal structure, if we know the symmetry information and all those things. And if we from using that we can calculate the structure factor, we can calculate the multiplicity factor, etc. And we have the Bragg's law, which will tell us that exactly where we will be getting for a particular lambda value, where we are going to get the X-ray diffraction pre. So, we can virtually we can construct the X-ray diffraction profile for any material if we know the crystallographic information. But then we have seen that a real specimen, the X-ray diffraction profile of a real specimen is quite different from the one that is generated theoretically by this method, structure factor, and then using structure factor and using Bragg's diffraction law. The most important difference is that whereas if you construct it theoretically, you will be getting a line function. Whereas in a real specimen you have a finite width for this X-ray diffraction peak, and there are other differences like the diffraction intensity will not follow the trend and so on. But this broadening of the peak or a finite width of the peak expressed in terms of FWHM, that is what is basically a representation of various effects that is causing that. And if we understand what are these effects that is causing this widening increase in the width of the peaks, then we will be able to understand many more things other than crystal structure, many more things we will be able to understand from that X-ray diffraction profile. So, that is what we started, and the first thing we did is to understand the effect of the line instrumentation broadening, the width broadening of this X-ray diffraction peak caused by the instrument itself because of this non-monochromatic beam, non-parallel beam and so on. And then we started understanding slowly the effect of the size of the specimen, the size of the crystallites, which is basically coherently scattering domains which are responsible for the X-ray diffraction, for causing the X-ray diffraction, and the smaller this domains becomes or this crystallite becomes, the peaks gets widened, we understand that. And then we started discussing about another effect, that is the effect of strain in the material, and we will continue that in this lecture as well, the effect of strain. And then we will see another important factor, that is the amorphous and crystalline difference between amorphous and crystalline materials. And finally, we will discuss about the various possibilities of using this X-ray diffraction data very briefly, not going in any details about that. Okay. So, the first thing is effect of strain, and in the last class we started that how initially people thought that even the crystallites are divided into further smaller structures, and these structures they called it mosaic structure, where mosaic structures are around 100 nanometer of size and misoriented by at the max 1 degree angle. So, these small domains or small subcrystallite domains, they thought that is responsible for the widening or for increasing the width of this X-ray diffraction profile. And after the discovery of TM or after the discovery of transmission electron microscopy, when people started seeing the materials in great details, their internal structure, people were trying to or people were able to see, then they understand that these mosaic structures are basically the structures, or they resemble very well with the dislocation structure. The dislocation, if a material is heavily deformed, then and containing huge quantity of dislocation, huge dislocation density, then those dislocation goes and form their own structure within the material, and then those structures size wise and the misorientation wise, those structures were very much resembling to this mosaic structures. For example, if you see this TM images which is showing the dislocations, which are basically these black lines. You can remember our discussion about the dislocation contrast. So, these are taken at this dislocation contrast, and what you can see is that dislocations are forming very nice boundaries here, which are known as the subgrain boundaries. So, basically when the dislocation density becomes very high, those dislocations forms this kind of boundaries within the materials and further divide any grains, original grains, they further divide it into smaller subgrains, and within the subgrains these areas are very much dislocation free. So, all the dislocations are accumulated at these boundaries. That means the dislocation density or dislocation distribution becomes very non-uniform in those kind of materials, and size of this, as I said, size of this dislocation cell, this is called a cell structure, dislocation cell structure, and this also evolves basically as a function of applied strain. The dislocation structure also evolves. Initially you have this band like structure, and then you have the cell like structure, dislocation cell. So, this is different stages of evolution of dislocation structure, but whatever it is, what we understand is that this kind of a structure is basically similar to mosaic structure, and now onwards we will not be using the term mosaic structure, we will be using the dislocation substructure. Okay. So, what does this dislocation substructure does? And remember, the misorientation between these structures are very less, and that is expressed by a term eta. So, that is the amount of misorientation between individual dislocation subgrains or cells, and that eta is within 1 degree. Okay. Now, if we put that in this n lambda equals 2d sin theta, and we imagine that we are working with a perfectly monochromatic beam, perfectly parallel, perfectly monochromatic beam, then just because we have this dislocation cells which are disoriented within themselves by a very small amount, what we will be getting is that we will get considerable intensity not only at the Bragg's condition or the Bragg's angle theta b, we will get it for an angle theta b plus eta. So, for theta b plus eta, eta being very small, we will be getting considerable intensity from this, because and this non-monochromatic beam and little bit non-parallel beam adds to this. So, if you have a non-chromatic beam anyway, it will be allowing little more Bragg's condition to be satisfied for a much relaxed condition, and that relaxation increases even with eta as well. So, ultimately what it will does is that it will cause this line functions, it will cause them or to be a finite width just because of this dislocation cells being there. So, as a whole, the strain, so dislocation structure means strain, basically the strain in the material that we are imparting on the material is causing the dislocations to evolve or dislocations to generate in the first place, and then the dislocation structure to evolve. So, the dislocation substructure is a manifestation of the applied strain. So, we can say that because of the strain in the material or strain, or in other words we can imagine that the strain is or the material contains that applied strain in the form of dislocation substructure. So, the effect of strain is basically going into broadening this X-ray diffraction peak. The more amount of strain or deformation we put in the material, the more rapidly this dislocation structure will evolve, the size of the dislocation structure will become smaller, and so on and so forth, and the more broadening will be caused here. So, this is what the effect of strain largely we can think of is the effect of strain in the material and it is causing this dislocation substructure, and then the dislocation structure, because of their small size and very small amount of misorientation, causing the X-ray peaks to be broadened by certain amount. Now, we have to understand how that stresses or strain is evolving or appearing in the material. Now, this is what the root cause, the dislocation substructure, but we have to see that how the stresses are reflected finally in the X-ray diffraction profile. So, we can basically divide the stresses in the material, in any material when we are putting some strain and we are getting some stresses, some dislocation structure. We can imagine that there are two types of stresses which can be there in the material. One is the micro stresses and the macro stresses. So, micro stresses or correspondingly the micro strain, whatever you can call. So, micro stresses or micro strains, they basically varies from one grain to another, or even within one part of the grain to another part on a microscopic scale. That means on a submicron scale possibly, and if you think it in that way, if you have a submicron size grain, even within the grain you have this dislocation substructure formation, and that dislocation substructure even varies with grain to grain, because many different grains may have different orientation, and dislocations of course will be completely different, type of dislocations will evolve, dislocation density will be different, so on and so forth, whatever it is. So, basically we can imagine that this is happening, a strain accumulation is happening in the material at micro scale. Compared to that, the macroscopic stress is basically the stress you are applying on the overall material. So, all the grains collectively together, if they have a quite uniform stress over a larger distance, we can call that as a macro stress. Basically, it is the stress you are applying to the material, and the material is showing the effect of the stress over a larger scale. So, if you think of this to be a grain, complete grain, and this grain is having now different regions with different orientation, different dislocation subcells, you can imagine, and the macroscopic stress is possibly applied on the all the grains or all of these grains, smaller grains, the macroscopic stress is applied, and in microscopically these individual grains have a different amount of microstress. So, ultimately what you can imagine, the macro stress and micro stress basically does not correspond 1:1. They are not, it is not like if you increase the macro stress, the micro stress will increase, because that is, these two are governed by completely two different length scales altogether, both in the microstructurally and as well as in the mechanical respect. So, completely different length scales are involved in these two type of stresses, micro stresses and macro stresses, and that is what it is shown here, that if you look at a annealing with a titanium alloy billets, the way macro and micro stresses varies with annealing, this is completely different. So, when the micro stresses are high, macro stresses the macro stresses are very high, micro stresses is still very low, and when the macro stresses are something like started dipping up, the micro stress is becoming increasing, or it is becoming higher. So, this kind of relationship we can get between the macro stress and micro stress, but ultimately we can imagine that any material would possess two types of stresses, one extending to a larger distance, several grains, or in the bulk scale, another one is possibly within the grains, within the grain itself, or at that kind of a length scale. So, these are the two kind of stresses, at least from an X-ray diffraction, the way they are influencing the X-ray diffraction profile, from that perspective we can think of these two type of stresses. Now, let us see that how these two stresses are acting on the X-ray diffraction profile, what is their effect, what does they do, and how we can make out the extent, or this entire thing is, by the way, is basically determined from the X-ray diffraction profile, both the macro stresses and the micro stresses, and we can think of, or we can discuss about how these things are determined. Okay. So, let us imagine this is the normal regular crystal or normal regular grain, one single grain at equilibrium condition, there is no stresses applied on this material, and this is having something like an interatomic spacing which is d naught. Okay. So, because of that we are getting now this X-ray diffraction profile without any broadening, in the sense without any broadening due to strain, whatever the little broadening we are having it over. So, this is the 2 theta which is from the Bragg's law, the ideal condition what we are getting, exact Bragg's angle where the diffraction condition is satisfied and we should get highest intensity, right. So, this is that line. So, if we do not have any stress on this material, this will show exactly a X-ray diffraction peak with a maximum intensity corresponding to the exact Bragg's angle, and this whatever broadening we are seeing here, that is possibly because of the instrument or because of the size, we are getting a finite broadening here. Now, let us imagine we are applying an uniform tensile strain on this material. Tensile strain means we are basically elongating this material. So, now what is happening, this d naught is increasing, the atomic planes are going further apart from each other. So, d naught is basically increasing. If we put that and keeping all other condition constants, that means lambda becomes constant. Now, we will be getting a sin theta which is lesser than the theta b, the earlier Bragg's condition, exact Bragg's condition. The sin theta will be smaller because d is increasing. So, what will happen is the entire peak will be shifting towards the left. Okay. So, that is the effect of a macroscopic strain or macroscopic stress. If you are applying the stress on all of the grains, on all of the atomic planes, then the entire peak is shifting towards left if you are applying a tensile strain. If you are applying a compressive strain, then the d naught will decrease. That means all the interatomic planes, all the planes will come closer together, interatomic distance will decrease, sin theta will increase, the entire peak will be shifted in the right hand side from theta b earlier for a condition where there is no strain. So, that is an effect of macro stresses that you can imagine what the macro stress will do to your X-ray diffraction peak. Without affecting the intensity, it will just shift the peak either to a lower value or a higher value depending on whether you are applying a tension or a compression. Okay, fine. Now, let us imagine another situation where we are applying a bending. Now, instead of a tension or compression, we are applying a bending. We are bending this entire crystal. What will happen? We will get a tension on the top side and a compression on the bottom side. So, this is like a 3-point bending, you can imagine 3-point or 4-point bending. We are getting a tension on the top side and a compression on the bottom side. So, within the same material, within the same crystal, if we imagine this is to be one single crystal or a grain, whatever. If we imagine that, then within the same grain or same crystal, we are getting now two different regions where one is a tension, one is a compression, and the tension and compression is also constantly varying with a distance. So, what will happen is at certain regions the material will have interatomic spacing higher than d naught where the tension is prevalent, and where the compression is prevalent the material will have a interatomic spacing which is lower than d naught, and at equilibrium at some intermediate condition where there is an equilibrium stress, no stress, zero stress, it will have something like d naught, the interatomic spacing will d naught. So, now this entire material is divided into different stress state. That means we are now generating a micro stress in the material, not a macroscopic stress. We are generating a micro stress in the material. So, how that affects micro stress? Okay. We immediately understand d naught is now different. Some places d naught, the interatomic spacing d is greater than d naught, some places d naught or interatomic spacing is lower than d naught. So, what will happen is that some regions, because of the d naught being smaller than or d being smaller than d naught, we are getting peaks will be forming higher than theta b, or some regions, tension regions where d naught or d is greater than d naught, the peak will try to form at a lower sin theta value than theta b. Ultimately, this will affect in a larger broadening of the peak, and intensity will also correspondingly decrease. So, that is the effect of micro stresses. Micro stresses will broaden the peak as well as it will decrease the intensity of the peak. Macro stresses will just shift that peak position. It will not cause a broadening, neither it will cause a neither it will cause a decrease in the intensity. Now, these are the two extreme cases, and this is not what we can expect in a real sense, that there will not be any macro stress, only micro stress, or there will not be any micro stress, only macro stress. These are the two extreme conditions that we are dealing with. So, in real conditions, if we look at this kind of a situation where this is the XRD pattern of a ball mill TiO2 powder for different milling times, and this is the corresponding, this is one such peak, 101 peak, and what we can see is that as we are increasing the milling time, so more and milling time, increasing milling time is more and more strain is imparted on the material. So, what we are able to see is that without the milling, this is the peak position. So, exactly at the Bragg's condition, the moment we started the milling, now the peaks are getting shifted, the intensity slightly decreases, but more prominent effect is peak shifting towards the left. So, there is considerable amount of macro stresses generated in the material at the starting. When we are continuing this milling operation for more and more time, then we are generating much more amount of micro stresses as well. Because of that, now the peak intensity is decreased, and as well as the peak is now getting broadened. So, more than shifting of the peak, this is now showing more amount of broadening. So, that is why we can call that now micro stresses are more prevalent at when we come or when we go for a longer annealing time. So, basically this is what again showing the effect of the initially it is basically macro stresses, and towards higher annealing time it is milling time, it is basically the micro stresses which are more prevalent, but all the times both the stresses are there and together they are playing, but they are not going hand in hand, which we already saw here the macro stresses and micro stresses are not going hand in hand because of this kind of effect. Anyway, so how to get the quantitatively, how to get this amount of stresses in this material? There are many other ways, but we are discussing about the most simplest of all, how we can determine the amount of stress in the material. Okay. So what we can do is that we can take the Bragg's law and just we can differentiate. So we can take this n lambda equals 2d sin theta. Well, lambda we can consider lambda being constant and n being just a first order diffraction. So n is 1. So if we differentiate that, what we are getting is the width of the peak, which is basically delta 2 theta. Means if you remember our discussion in the last class, the theta 2 theta 1 minus 2 theta 2, that is the broadening, and ultimately we were getting b equals theta 1 minus theta 2. So same thing we are now getting here, that we are expressing delta 2 theta and we are differentiating this entire Bragg's law. What we will be able to write here is basically minus 2 delta d by d into tan theta. So this b, the broadening, extra broadening due to the strain over and above the instrumental broadening or size broadening, the broadening caused by the strain is equal to minus 2 delta d by d into tan theta, and delta d by d is basically the amount of strain. From the definition of strain, delta d by d, delta d, so this is, if you know, strain is basically the change in the dimension, if any of the dimension, the change divided by the original strain. So that is the original length, that is what we can express that to be a strain. So this is the strain, so we can write eta if we or some other value. So we are writing delta d by d here, this is the strain into tan theta. So from this we can determine the amount of strain in terms of the width. So tan theta, of course, theta is the theta b, we know that from the diffraction, this curves, we know the theta b, and from by measuring the width of this or the broadening of this peaks, we can determine the amount of strain present in the material. So this is how we can get basically the micro strain in the material. For measuring the one more important thing is that this strain, basically this strain includes both tensile and compressive. So you can imagine that micro stresses, as I just gave an extreme example, the micro stresses contains both tensile and compressive, and if we imagine that both of them are the same, the amount of tension is exactly equal to the amount of compression, that is why we don't get any macro stresses. Tensile stresses in the material is exactly balanced by the compression stresses, and we don't get any amount of macro stress. If that is true, that is an extreme, of course, it is not a reality, but that is, in that case, what we can imagine that this micro strain is basically composed of equal amount of tension and compression, and we can get either tension or compression just dividing this by 2. So that is how we are getting micro strains, either compressive micro strain or tensile micro strain, which is also done here. If you look at here, this is the tensile and compressive part of the micro strain. So one part is tension, one part is compression, and of course the here we are the assumption is that both of them are exactly equal in tension and compression. Otherwise, but that is not something what we see in reality. That is why we are finally getting some macro stresses in the material. For macro stress, determination of macro stress, that is a comparatively difficult one to do. Basically, you have to rotate this material, that is something related to the residual stress determination and so on, which is related to the rotation of this specimen along some specific axis, phi axis, psi axis, and that is how you can generate something called rocking curves, and those rocking curves will give you the amount of macro stresses. We are not going exactly how this is done, the residual stress measurement and so on. If you are interested, you can always go through the reference books. Okay. So now that is what is strain is doing. We will be discussing one last effect, which again will change the extra diffraction peak. So this is basically amorphous versus crystalline material. So about the structure or about the atomic arrangement within material. So this we have discussed a little bit of that when we were discussing about, if you remember, we were discussing about the Bragg's law. We discussed how crystalline periodic arrangement, how that is finally responsible for getting the constructive interference and so on and so forth. So for a solid material, we can imagine solid crystalline material, we can imagine and completely periodicity in the atomic arrangement. All atoms are fixed around their mean position, and we have a complete periodicity in the material. For liquids, of course, the atoms are not having the periodicity. Liquid or amorphous structures we can think of that they are not having this periodicity, but they are still tightly packed together, and this shows a statistical preference for a particular interatomic distance, which we can identify from something called radial distribution function. Basically, we are not going into that, but for amorphous material we can find out, we can express the same thing using radial distribution function. So, their radial distribution function, basically what it tells is that this interatomic distances, even in a liquid material or an amorphous material, supercooled liquid, this interatomic distances are not any random value. There is a preference for certain interatomic distance values. So, that means this has certain level of order at certain length scales, of course. Monoatomic gases, we can imagine that that length scale is really large. That means the material, the atoms are completely randomly oriented. There is no periodicity, and as such there is not any preference for interatomic distance to be with assuming some particular value. So, the way this is affecting, of course, because of this atomic arrangement, we have already discussed how this atomic arrangement is responsible for producing this kind of a crystalline peak, this kind of a peaks at well defined angle for a crystalline material. Constructive interference will happen only along certain particular angles. Rest of the angles it is supposed to be destructive interference, but of course there will be some measurable intensity because of other factor. We have discussed thermal scattering, how it attributes to the finally to your to the background of your material. So, basically the crystalline material, you will be expecting this kind of sharp peaks in the material. For liquid, if you take an X-ray diffraction peak, now what will happen is that the interatomic spacing is continuously changing. So, between various atoms, you are having a completely different interatomic spacing. Of course, they will be statistically they will be having a preference towards one single value, but that will also be a large range. So, correspondingly what we will be having is this kind of an X-ray diffraction peak, where you will have a very wide and broad peak in the material. So, this is you can think of as in one extreme of this size effect. So, here the size is so small and size is varying in such a large way that you are getting a huge kind of broadening for individual peaks, and then finally what you will be getting is one single peak possibly, which is very, very wide. And the extreme case is of course the gaseous material, where the X-ray diffraction peak is possibly will vary like this. It will start with a higher intensity and it will continuously keep on decreasing. Now, the one point you should understand for a monoatomic gas, even for a monoatomic gas, you are not getting a completely horizontal, you are not getting any X-ray diffraction at all. What you can imagine for liquid or monoatomic gases, you can imagine this is more like a X-ray scattering, not a diffraction. Diffraction we discussed, it is a particular case of this scattering where we have this constructive interference phenomena happening for a certain particular direction for this X-ray scattered X-ray beam. That is not happening in case of a liquid or monoatomic gases. In this case, the X-ray intensity, the intensity of the X-ray is basically varying from a high value to a low value because of the atomic scattering factor. So, if you remember, the atomic scattering factor varies in this way with respect to the sin theta and lambda, and for a monoatomic gas, basically whatever variation you will see with 2 theta, the intensity of the X-ray beam is exactly because of this variation in atomic scattering factor with sin theta by lambda. So, that is how we are getting a difference between crystal and an amorphous material, and the extreme is a monoatomic gas. Okay. So, with this we are getting over. So, we will be checking some if you can use this information that how the X-ray diffraction profile will change from a crystalline material to an amorphous material. You can use that for various studies. One such we are showing it here. So, you have the glass that we do in our research group. So, this is an X-ray diffraction profile for a base glass, and you can see it is just similar to this liquid where you are getting one single very broad peak, and mostly you get the background, you do not get any sharp peak. Now, if you know the glass is a metastable state, it is a supercooled liquid, and for some glass systems you can basically promote crystallinity into this. If you do a heat treatment, secondary heat treatment on the glass, you can develop crystals within that glass itself. So, if you do that, then slowly you are doing a heat treatment, and slowly you are increasing the crystal volume fraction, you are generating crystal within that glass, and that will result into this sharp crystalline peak. So, if you you are starting with this base glass with no sharp peak, and you are ending with a completely crystalline material with very sharp peak. So, if you just take or if you monitor this process, you can be able to see this change in their corresponding X-ray diffraction profile. Okay. So, this kind of studies you can do it, and this is the last thing that we can possibly discuss about this X-ray diffraction profile, X-ray diffraction course, part of this course. Various possibilities of using the X-ray diffraction data. So, now you can see that this is the kind of specimen or this is the kind of X-ray diffraction profile that you can get from a real material. From this, of course, what you can do is the phase identification. If you do not know what phase it is, then you can try to find, or if you have a mixture of various phases, multi-phase material, mixture of various phases, then you can find out exact phase, which phase it is from your X-ray diffraction profile. You can do crystal structure determination, of course, but normally crystal structure determination is done with single crystals and by some other method, but from an X-ray diffraction, but the main underlying phenomena is the X-ray diffraction profile. So, crystal structure determination also you can do. If you do not know the crystal structure of any unknown material, you can do an diffraction, and since diffraction is related to atomic arrangement, which you by now you must have understood, you can determine the crystal structure. Okay. And then similarly for phase identification or for crystal structure determination, the next step is to determine the lattice parameter for this material. Accurate lattice parameter determination you can do. For example, if you are working with semiconducting materials or if you are working with the thin film deposition and so on, then you can think of or you can find out that how the lattice parameter changes with change in composition, change in your parameter of deposition and so on and so forth. So, all of these things you can do with X-ray diffraction data. Basically the Bragg's law where you determine the D value. You can of course do the crystallite size determination. If you have a nanomaterials or if you have an ultra fine grain material, you can determine the crystallite size using the Scherer formula or using much more advanced techniques are there, Rydberg definement, or you can do MWP, multiple hole profile fitting. All of these methods you can use, find out the crystallite size. You can determine the microstrain. You can go ahead another stage and you can determine the dislocation structure on the material, again from this high end methods. You can use some very simple methods known as Williamson-Hall method, or you can go for very high end methods like this MWP, CMWP, all of these methods. You can go for a residual stress measurement, which is like the macro stress measurement which I discussed. You can do this specific rotations. You can use something called Euclidean cradle. You can give some specific rotation to a specimen, and from the peaks, how the peaks are varying, X-ray diffraction peaks are varying, you can determine the residual stresses in material, and you can of course determine the orientation and crystallographic texture, again by giving some particular rotation, which we also do, which we very regularly use in our research group, crystallographic texture determination, but those are like a little advanced. The underlying phenomena is of course the X-ray diffraction, but there you have to go for even a little higher in terms of instrumentation. You have to give specific rotations in the specimen, and then you can determine some other things, which like you can determine something called pole figures, you can determine orientation distribution function and so on. So, we are not going there. You can use X-ray diffraction in terms of phase transformation study. We have already shown you one couple of example, like you can check out this gamma to alpha, or as a function of temperature how your different peaks are coming up, and from there you can identify this phase transformation, which phase is transforming to what is their orientation relationship and so on and so forth. You can determine by in situ study or by ex situ method, you can determine a phase diagram, you can determine the change in the crystal structure as a function of temperature or pressure. You can find out the quantitative phase fraction determination, which is very useful for people working in steel industry. They often ask us to determine the retained austenite volume fraction. That's what they call it, that how much austenite is retained in the material after at room temperature. And from X-ray diffraction you can find out, this is something like to do with the intensity of the X-ray diffraction peaks, and then do a quantitative phase fraction determination. You can also use it for determining your crystal quality determination. If you are developing a single crystal, you can take an X-ray diffraction and find out that how much order is there, or what is the imperfections are there in your crystal and so on. And there are endless other possibilities exist where you can use this X-ray diffraction data. So, X-ray diffraction is possibly one method which is very useful and very powerful method, developed possibly long back, almost 120 years or even more than that time X-ray diffraction, but still people are using it, and there are many other many other applications possibly you can think of where you can use this X-ray diffraction data. I request all of you to go through the reference books to know more about the possibilities or more about what you can do with this X-ray diffraction data, and of course, we will be happy to help you to if you have specific queries to know where you can use this X-ray diffraction. So, with this we are ending this X-ray diffraction part. We have one more lecture left, and there we will be discussing some special topics in the next class. Thank you.